Okay, so welcome back. This is our third lecture on Calculus 1, and we're going to begin by finishing what we started last time. We're going to look at a few theorems involving limits, learn how to work with limits algebraically, take a break, and then move on to the next topic. Okay, so I'm assuming that all of you are caught up with basic definitions of limits and have watched the previous video or attended the previous lecture. So to get started, we need to write down a theorem. So if the limit of some function, say g of x, as x approaches c, is equal to L, and the limit as x approaches c, or not c, as x approaches L of f of x equals maybe capital K, then the limit of the composition as x approaches c, so f composed with g of x equals k. So this is a theorem about composition of functions. Now, recall composition, you can evaluate a function at a whatever numerical value you want, and that numerical value can be the input, the output of another function. Okay, so this business right here is the composition, which some of you might remember from like college algebra or pre-cal as f composed with g, using that notation, like that. And this theorem states that, come on, camera focus. This theorem states that the limiting process will pass into the composition process. Okay. Now, this is important. It might not seem important to you. It might seem a little esoteric, a little random, like a lot of things in your math courses are or seem. But this is actually really important when looking at derivatives of composition functions. And this thing called the chain rule that we'll encounter in a few weeks, or maybe in a few weeks. And this chain rule is probably one of the most important tools that I use as a practicing data science doing what's called machine learning. So in these like machine learning models, these deep learning models, composition of functions is very important. And taking limiting processes or approximating these limiting processes for what's called derivatives it's why a lot of the things that work on why a lot of the things that are on your smartphones do what they do. And I'm actually going to make a point of that when we get to that part of the semester. But just know for now, composition is important and it actually is useful. So, but for now, as far as like homework and maybe an exam goes, let's just look at how we can use this theorem. So let's look at an example. I have two examples. So maybe we want to look at the limit as x approaches 0 of square root of x squared plus 4. Okay. Now we can think of this as a composition of functions, right? So, for example, this isn't. Well, maybe this would be a way that you would write a solution, but I'm going to go through the details of how we can apply that theorem to this special case. So notice that if we let g of x equal to x squared plus 4 and f of x equals to root x, then this argument here is precisely that function composed with that function, right? So I'll just say like root, well, maybe I'll write f composed with g of x is precisely that. Right? So what do we plug into f when we're composing? We plug in g of x. So instead of writing an x right there, we would write g of x, which is equal to that. So this we can think of as a composition of functions. Okay? So by this limiting theorem, we have, so if g of x converges to some number L as x approaches c, and as x approaches L, f converges to some number k, then the composition will converge to k. So what's the limit as g of x approaches 0? So limit, so not g of x, as x approaches 0 of g of x, well, that's just a polynomial function, right? X squared plus 4 is a polynomial, it's smooth, there's nothing to worry about. And as we learned in the previous lecture, we can just plug in that limit value into the polynomial, and that will be the resulting limit. So we plug in a 0 there, we get 0 squared plus 4. So that's just a 4. Okay. Then, making use of this theorem, right? Like if as x approaches 0, g of x equals L, this is like our L right there. Then we have to consider f now. Where does f go as x approaches L? So the limit as x approaches 4 of f of x, which is this, right there. Now again, as we learned in the previous lecture, this radical function, this taking the square root of x, the input is positive, so we don't have to worry about anything weird happening when evaluating the limit. So we can just literally plug that in as our argument, and we get square root of 4, which is just 2. So by this theorem here, we have that the limit as x approaches 0 of the square root of x squared plus 4 is equal to 2. And that's by this previous theorem. Okay. So this is just another way of evaluating limits, and we're kind of coming to the end of the different methods or theorems needed to evaluate these limits with this one. Now, I was going to do an example B, but for the sake of time, I'm just going to go ahead and move on. And hopefully this weekend, I'll be able to, like I was mentioning last lecture, give you a bunch of like problems that I solved by hand and just work them out so that you'll be able to see these examples. All right, next up, another theorem. Okay, so maybe we can say like, let C be a number in the domain of the, I'll just say following functions. So then part 1, if we take the limit as x approaches c of sine of x, this is just going to be equal to sine of c. So we really don't have to worry about any particular like issues. Just in my light so it's not so bright. With sine, right? Sine, there's no jumps or like any discontinuities that we need to worry about. So this hopefully would make sense. Okay. Now, actually, my lighting is pretty off right now. Let me turn on another light. That looks a little bit better. Okay, so lighting's better. So hopefully, back to this, sine of x, taking the limit as x approaches c, it should make sense that this would be sine of c. Second, the same should hold, right, for cosine of x. Right, again, these are really, again, smooth. There's no jumps, no division by zero. So we should expect that the limiting value we should just plug in into the function. Now, for something like the tangent function, we have to be a little bit more weary of what it means to be in the domain of the tangent, right? Because, well, I'll just go ahead and write it out. Tangent of x is defined as sine of x over cosine of x, right? Now we know something from the previous lecture about ratios of functions when taking the limiting value. Provided those limits exist, we can write the ratio as long as the denominator is non-zero. So we can just plug in c for both of these, but make a note so we have to be careful about this, provided that cosine of c is not equal to 0. Okay. And then in a similar fashion, we can continue writing out this theorem to get cosecant, secant, and cotangent limiting values. You just have to be very careful about where x is going to, because division by 0 will occasionally happen, right? Especially when looking at tangent or cosecant or secant. Because all of those other basic trig functions are defined in terms of these two guys, right? Like cosecant and secant are 1 over one of those, so you have to be careful about when you could possibly divide by 0. Now, just to kind of refresh your memory about when cosine is equal to 0, just remember that on the unit circle, cosine is the x value, sine is the y value, right? So when are the spots where the x value on the unit circle would be 0? Well, there, which that's at an angle of pi over 2, and then it would also be 0 right there, which is 3 pi over 2. And that, in fact, starting at pi over 2 and adding any integer multiple of pi will give cosine of c equal to 0. So those are the values that you'd have to ignore when considering this limiting value for tangents. Okay. All right. So those are the basic trig functions. All right. Another theorem. I swear we're almost done with these theorems and we can just work through some problems, but the theorems are important. Okay. Okay. Next theorem. let f of x equal to g of x for all x equals c, or x, sorry, not equals to c, in some open interval containing c. Okay, so what's the picture that you should be imagining with the statement of this theorem? Well, on some open interval, they're the same function except at one spot. And that one spot is precisely x equals to c. So I haven't stated the actual conditional of that theorem, but I just want to make sure that you're on the same page before I write that down. So, for example, maybe we could have like, this is G, and here's C, and then F looks the exact same except at x equals to c. Okay, so they're basically the same thing, with the exception of maybe like 1 point. And maybe for some reason it's like a piecewise function on f, and it differs at x equals to c right there from g. Okay, so in this case, we can say if the limit as x approaches c of g of x equals L, then
I'm trying to pause it, like I can't pause it.
the limit as x approaches c of f of x equals L. So that's the full statement of the theorem. Now, hopefully this should make sense, right? Because if we look at the behavior as x approaches c from this direction and from this direction of g, as we're heading this way or heading that way right there, the function's values are heading towards some value there, L, right? Now, because f is the same function as g, with the exception of that 1 point, just excluding that 1 point, f is going to behave the same way as g. It's going to, as we're approaching c from this side and approaching c from this side, f is also going to approach that same number, which means that the limiting value will be the same. Okay? So I think like maybe what would this function, I think I have an example. Oh, so this picture might correspond to something like this. So we can say f of x is equal to x cubed minus 1 over x minus 1. And then say that c is equal to 1. Okay, so in this case, f is not defined at x equals to 1, which means that there would be a little hole right there in the graph of f. But then the graph of g, well, it seems like there might be like a way to factor this that you might have encountered in pre-cal or college algebra. So let's rewrite f and see if we can factor it and get rid of that removable discontinuity. The resulting function that you get will be exactly g. So this will be x minus 1 times x squared plus x minus 1, and then all over x minus 1. Oh no, plus 1 is the minus 1 right there. And if you check this, this polynomial times this polynomial is precisely x cubed minus 1. So then we can divide out this 1 here. X minus 1 divided by x minus 1 is just 1. So we're left with x squared plus x plus 1. And that, in this picture that I've drawn, that would be your g of x, right? G of x would be that smooth parabola where there is no discontinuity, but f has that discontinuity. It's that removable type of discontinuity. So then, because these are the same function except they differ at c is equal to 1, we could apply this theorem and say that the limit as x approaches 1, that's the c that I chose there, of x cubed minus 1 over x minus 1, which is just the f, is equal to the limit as x approaches 1 of this thing, which is really simple to evaluate, right? This is a polynomial. For polynomials, we know that we can just plug in the limiting value by a previous theorem. So plug in a 1, we get 1 squared plus 1 plus 1. So 3, right? But again, hopefully it makes sense if you understand the limiting process, because they only differ at c. They're going to behave the same way as x approaches c. Okay. All right. Next up. So there are some techniques that you should be aware of other than the theorem techniques, or the applying the theorems to limits of functions. And these, the two that come to mind immediately are being able to factor rational functions to eliminate, just like we did here, to get rid of the removable discontinuities, and then we can apply this theorem. So maybe I'll do that one first to reiterate that process, and then I'll show you the next technique. So let's call this technique factoring limits. So suppose you wanted to evaluate the limit as x approaches -3 of x squared plus x minus 6 all over x plus 3. So if you see any type of rational function, again, rational functions are ratios of polynomials. That's a ratio of polynomials. Because of this theorem, if we can remove one discontinuity from this, because there's obviously a discontinuity x equals to 3, if we can remove that by factoring, then we know that we can find the limit by applying this theorem. So can we factor this? We're heading towards -3. So factoring the numerator, so what times what equals -6, that together add to the coefficient of x there, which is +3 and -2. So we can factor. So this would be x plus 3 times x minus 2 in the numerator. And in the denominator, x plus 3. So now this piece here, this would be like our function f in the previous example. And then x plus 3 divided by x plus 3 is just 1. So we have 1 times x minus 2. So if we remove that, we get that. So this function in the previous example would be like our g of x. So that function and that function there differ at exactly one value. X equals to -3. So we know that the limit of this is going to be equal to the limit of that by applying that theorem right there. So this limit here is just -5. Okay, so it's important to remember these factoring steps, especially something simple like that, because they will appear and it makes life a lot easier if you can reduce it to something that's easy to evaluate. And again, we're able to do that because of the theorem that I just erased. All right, next up, oh God, what should I call this? Maybe rationalizing for limits, we'll call it that. So this is another technique that you might encounter in the homework or maybe on an exam, where you're asked to find a limit that has a rational operation in it somewhere. So for example, the limit as x approaches 0 of root x plus 1 minus 1 all over x. Okay. Now, I was kind of moving fast over here, so I'm going to take a step and pause. First, before you try to do anything, look at it and see if you can just evaluate the function, right? Like, if x is equal to the limiting value, do you have a problem? Over here, we had a problem of division by 0. Over here, we have the same problem, division by 0. Once you encounter a problem, actually, you get 0 over 0 here. That's a different type of problem. It's still a problem. Once you encounter that problem, then you can move to using factoring or this technique here. So starting with this, I'm going to multiply by a special form of 1. Right now, remember from algebra that you can always multiply an expression by 1 and nothing will change, right? So what I'm going to multiply is a particular form of 1 to get rid of that rational value right there in the numerator. So I'm going to multiply this whole value by square root of x plus 1 all over square root of x plus 1 plus 1. Okay, so again, this is a valid operation. I just multiplied this expression here, this function, by 1, nothing changed. So why did I do that? I did that because I know something about factoring. In particular, I know that, well, just in a general form, recall from algebra, that a minus b times a plus b is equal to what? A squared minus b squared. Right, this is a difference of squares formula, right? So notice that if I have a square root as my a, and then I square it by having some expression looks like that, the square root goes away. And then maybe something useful will happen. So this is now going to be the limit as x approaches 0 of, So in the numerator, I have a minus b times a plus b, which is equal to this, okay? So a minus b times a plus b in the numerator will be a squared, which gets rid of the square root. Recall that the square of the square root is, it goes away, right? So I'll have x plus 1 minus b squared. B in this case is just 1. So get that. And then in the numerator, I get x times all this business. I'll just distribute it out. So x times that value plus x times that value is just that. Okay. Now, what happens here? I probably need to continue over here. So I get the limit as x approaches 0. In the numerator, the 1 and the minus 1 go away. And then in the denominator, it looks like I still have a problem. We'll figure that out in a moment. Or do I? No, I don't have a problem. Okay, so that down there equals that. And it might look like a problem because we're still going to have division by 0 if we try to just plug in that x equals to 0. However, I should have left it without multiplying it, right? And you'll see why in a moment. So instead of distributing the x inside, I could have just written it like this, without distribution. So if I write it that way, which again, it's equivalent, like that, then everything becomes okay. Why is it okay? Well, notice that we have x divided by x. X divided by x is just 1, so we can cancel those x's out. Right. Limit as x approaches 0 of 1 over square root of x plus 1 all plus 1. Okay, so now if we evaluate this, it's fine, right? If x is equal to 0, that's just a 1, so we have 1 over square root of 1, which is 1 plus 1. It's just a half. So a little tricky and annoying, understandably, but when you're dealing with like real world type of problems, the expressions that you will derive from whatever data that you're observing will not always be so clean. And these techniques of using a clever multiplication by 1 to get rid of radicals and simplify, or factoring, they actually do matter to make applications of theorems that you might know useful. Okay. I think this is a good spot to pause the video. All right, so we're back, and we're now going to discuss a major theorem in calculus called the Squeeze Theorem. So anytime that you encounter a theorem that has a name, it's typically important and can be used in a variety of scenarios to derive other important consequences. So anytime you see something with a name, make note of it, especially if you're a math major. All right, so what does this theorem state? Well, actually, before I even do that, before I write the statement, let's talk for a moment about an idea. So here we have x, y. And suppose we have, I don't know, some function,
Wow.
call it h. Also, be sure to mute your mic unless you're going to speak up. Okay, so suppose we have a function h behaving like this.
Tengo una amiga que se fue a Venezuela, espérate de eso.
Someone's mic is on.
A ver cómo son.
Back to what I was saying. Suppose you have some functions behaving like this. And I'll call
¿Qué es
this
eso?
h.
Cabrón.
And then also maybe suppose we have another function called g. It's behaving like this.
Chévere eso. Póngale che a eso.
Talking right now. Who's talking? Or someone's mic is unmuted. Okay, so back to the theorem. So suppose we have like h behaving like this and g behaving like that. And both of these functions are approaching some limiting value called L. Okay, now both of these, the limit as x approaches c of h and g, it will be L, right? We can like clearly see that with the picture. Now suppose next that there's some function f. It's maybe behaving like this. And it can go anywhere it wants to after that. So that's my f function there, shown in red. But it needs some interval, maybe there to there.
I'm so happy.
F is bounded above, and I mean, when I say bounded above, I mean that the y value of f is no more than h, so it's bounded above by h, and then the y value is bounded below by the y values of g of x. So this function f is contained in some interval around the value c between h of x and g of x. So with this containment, what can we imagine that's going to happen? Right? Like, as suppose like we know that the limit of h of x as x approaches c is equal to the limit as x approaches c of g of x. Give it some value called L. But suppose we know that, and h of x is at most f of x, which is at most, oh no, sorry, had it backwards. So g of x is at most f of x, and then f of x is at most h of x for all x in some open interval containing c. That's what this picture is saying, right? F is here. Outside of this interval right here, it can do whatever it wants to. But in this interval containing this value c, it's always at most h and at least g. So what can we expect about the limiting value as x approaches c for f. If it's always between this and this, and both of those converge to the same limit L, what can we expect about the behavior of f? It should go to the same value, right? Like, if this property right here is true, then it's somehow squeezed between the values of the function h and the value of the function g. So this is what's called the squeeze theorem. And it states that if, say, g of x is at most f of x, which is at most h of x, on some interval containing c, open. Whenever I write open, or whenever I say interval, typically I am implying open, unless I state otherwise. So this is occurring on some open interval containing c. And the limit of g of x as x approaches c equals the limit as x approaches c of h of x equals L, then the limit of f of x as x approaches c is equal to L. Now, of the many different theorems that we're going to encounter that are what I would call like major theorems in Calculus 1, this I think is the easiest to pictorially describe, right? We have a function that's always between two functions that are converging to the same value. If that function is always squeezed between them, there's no other option for it, like it has to go to that same limiting value L. Even if for whatever reason, this function differed at one spot and L like jumped up there, it doesn't matter in the limiting process. So even in like my statement here, you should be wary of that this process, I mean, this inequality holds on some interval containing C, except possibly C, because C could like, f of C could like jump up here. But it doesn't matter if it differs at one point because of what we learned like 30 minutes ago. If this is different from the typical behavior at only one point, the point C, x equals C, it's not going to matter as that function tends towards that value. Now, this is actually useful when solving problems if you can become comfortable with bounding functions, which is something that you probably aren't used to. In most of the mathematics courses that you've taken, you've always had like equal signs, like this equals that, whatever. But generally speaking, when you're dealing with real world functions based off of real world data, the interesting problems out there, there's no equals. It's like approximately equal, at most this or at least this. So even though in your mathematics courses, you're always doing equal signs, equals, equals, in practice, one of the most important signs or concepts is the notion of being approximate, at most or at least. And I've even mentioned this in last lecture that before solving a problem, you should get an approximate idea of where the answer should lie, so that once you do your computation, you'll know that you're at least that close. So I think that we can best illustrate this with an example. Let's look at the limit as maybe x approaches 0 of the function x squared times sine of 1 over x. And see if we can somehow figure this out using this notion of being squeezed in between something. Okay. This is somewhat of a classic example, but a really useful one. So I currently cannot plug in x equals 0, right? I have 0 times sine of 1 over 0, doesn't make sense. So maybe I can use a squeeze theorem to get an idea of what's happening by approximating this function's value as x varies through whatever. So first off, just note that sine, regardless of what the input is, sine is always between what? +1 and -1. No matter the value that you plug into that function, sine is always between +1 and -1. So note that -1 is at most sine of x, which is at most +1. Right? That's the range, -1 inclusive to 1 inclusive. So I have some type of estimate on the value of sine of x. Estimate. I'm not trying to be precise, I'm just giving like, it's roughly in there, right? So now, knowing that, maybe I can write the left-hand side and the right-hand side as some function where I know the limiting value, and then also manipulate the inside at the same time to all coincide with this notion of being bounded above and bounded below by a function and another function. So to do that, I can multiply both sides of this inequality by x squared. And the inequality is not going to change because when we multiply inequalities by a positive number, which x squared is, when we do that, the signs of the direction of the inequality is not going to change. So let me just multiply both sides of this, or all sides of this inequality by that term and see what happens. So I get negative x squared is at most x squared times sine of x, which is at most x squared. That follows directly from this observation that sine is always at most this, no matter what the argument is. Oh, I have to be careful here. 1 over x. It doesn't matter what the argument is, but I want it to look like that. Important point. So now that I have this, oh, this function is always squeezed between negative x squared and x squared. And this guy in the middle, that thing I was just mentioning, is what we're concerned with. So we can apply the squeeze theorem. Negative x squared would be here, positive x squared is there, x squared times sine of 1 over x is in the middle. Okay, let's see what happens. So the limit as x approaches 0 of x squared times sine of 1 over x, what does it equal? Well, what's the limit here and the limit here on either side of this inequality? Well, the limit as x approaches 0 of this polynomial is 0. The limit as x approaches 0 on this side of that polynomial is 0. They match up, so they satisfy that condition right here, which means that since the middle term is squeezed in between them, that limit has to be the same as those. It has to be equal to 0. Because that goes to 0 and that goes to 0, and that's always in between them. So this is a prime example of how the squeeze function can be used to find the limiting behavior of a given function. Now, yes, that's important, but I think the more important aspect is that this is an example of using estimates. We're getting an estimate on this function right there. And then using those estimates, we're going to deduce behavior, which is different from your other math courses, because in your other math courses, you wanted to find equals. We're getting estimates and looking at trends as things change. In this case, as x tends towards 0. Yeah. So that will conclude our section on evaluating limits using limit theorems and the basics of just that definition. In the next video we record, we'll talk about one-sided limits and a very fundamental notion called continuity. So that'll end today's video.